Hello children, welcome back to the channel. A new day, a new topic, a new chapter. The chapter of gravitation. Now, first and foremost, we need to understand what does the term gravitation means. Now, this term gravitation or this word gravitation has been given to a particular type of property of the universe, by virtue of which each material body, that is to say any particle or object which has a mass, attracts any other particle or any other body having a mass towards itself. So there is a universal force which acts between any two mass particles in the universe. This particular universal or force is known as the gravitation. So if we have to define gravitation, gravitation is the force of attraction between any two bodies in the universe. Now when we say bodies, we mean it could be two galaxies as two entities. It could be two stars, a star and a planet, right, in the cosmic level. It could also be between these two planes. There is also a force of gravitation between them, which means that any two objects which has a mass will attract any other object. This particular plane will exert force on each and everything, the camera there, the board here, and everything else, myself included, everything else, it will exert a force of attraction towards itself. Similarly, any other object, for example the board or the pen, the sun, the moon, the earth, the solar system itself as a single entity, will exert force on each other, and that force is the force of gravitation. Okay, now this concept of gravitation is not new to you. You have already come across this in a junior class, class 9th, right? And also we have learned about some laws and we have applied these things. So what this particular video will be kind of a revision to that and a little bit of addition, so that we can adapt to the concepts now to the class 11th level. Now what happens here is that first and foremost we need to know that there is another term, and we also already know there is another term and we have already used the term, and that term is gravity. So how gravity is different from gravitation? See, gravitation, as we have said, is a universal force of attraction between any two objects. Now, gravity is actually not different from gravitation in the sense that gravity is also the force exerted by virtue of mass. However, when we say gravity, we specifically mean or refer the word gravity to our earth, which means the force which the earth attract any other material body, be it the apple in the famous anecdote of Newton and the apple, be it the moon, be it the sun, whatever gravitational attraction the earth exerts is known as gravity or force of gravity. Okay, so gravity is actually gravitation, however it is specifically used for earth. So earth's gravitational attraction is known as gravity. So the force of attraction between earth and any other object lying on or near the earth's surface is given by the term, or we use the word of gravity. So since gravity is a force, so if say this is the earth's surface and there is an object which is near the earth's surface, let's say this is an object of mass m. So since gravity is a force, so there will be a force of attraction on the object towards earth. This force is responsible for the object to be bound to the earth. For example, I am standing on the earth's surface because earth's gravity is pulling me down. Without earth's surface, I would have flown away. I don't know where. You'll know that. You already have heard such examples already, right? Anecdotes also. So what happens is that if there is a force on this, the force of gravity on an object near the earth's surface, then it will definitely accelerate, right? And that acceleration that is produced due to gravity is known as Acceleration due to gravity. So when an object is nearby Earth's surface, due to Earth's gravity, the object accelerates downwards, right? So when an object is allowed to move freely. Now when we say freely, we mean that there is no resistance to its motion, which means, say if I release this pen, it will move through the air, and the air offers certain kind of viscosity, a resisting force. However, we are discarding that. If we are discarding that and we say that the object is allowed to move freely, in that case the Earth's pull will generate kind of an acceleration to the body, and that acceleration is known as acceleration due to gravity. So acceleration due to gravity is the acceleration produced by the Earth's gravity on an object nearby its surface when the object is allowed to fall freely. So when we say fall freely, what we mean is that free fall of an object. What is it? When the object is not bound to anything else anyway, in any ways, and is allowed to move solely under the influence of gravity. If we consider there is no air resistance or any other kind of resistance to the object's motion, that object, the object that moves under gravity freely without any other intervention or without any other force resisting or assisting its motion, we say it's under free fall. Which means, if we consider that air resistance is nil, so if this is Earth's surface and we release an object from here, initial velocity must be 0. Then the object will be freely falling. However, if I give it an initial velocity, which means I have applied a force, then if there is an initial velocity given in the downward or the upward direction, which or any other direction, the object will not be falling freely. Free falling means that the net initial downward acceleration should be 0. No, sorry, initial downward velocity must be 0. We are not giving any velocity to the object initially. It will be released from 0 velocity and it will allowed to move under the influence of gravity. Okay. So what we have discussed now till now is that what is gravitation, what is gravity, which is a special case of gravitation that applies to Earth and objects lying near the Earth's surface, and the acceleration produced by gravity is known as acceleration due to gravity, and a free fall of an object, when an object moves solely under the influence of gravity without any other forces acting on it. Okay. Now we have arrived at a position where we can start discussing the very famous Newton's law of gravitation. Now, the anecdote of Newton and the apple, whether it's true or not, we all have heard about that Newton was sitting in an orchard and then suddenly an apple fall, and that gave him the idea. What idea? That the apple falls to the ground because of some force, the force of attraction on the apple by the earth, right? So what if the same force is responsible for the moon moving around the earth, or the same force is applicable to all other celestial objects also? That idea is very instrumental, and this anecdote, whether it's true or not, however, it gives a very simplistic way of understanding that. So let's start with assuming that, or let's get into Newton's rules and then try to analyze this thing. So what he thought is that, let's consider the case of moon moving around the earth, right? So we have the earth here, has certain radius, and then moon is moving around it in certain in a orbit. What he considered is that the moon is moving around the earth in a circular orbit of some radius. Okay, let's say this is the moon. Now, clearly, since it is moving, let's say it's moving in the clockwise direction, the moon will have certain velocity, constant velocity. Let's call this velocity Vm, and there will be a centripetal acceleration. For the moon to be moving in a circular orbit, for an object to be moving in a circular orbit, there must be an acceleration acting towards the center of the circle, where the Earth lies in this case. So there will be an acceleration of the moon in the direction of the Earth, and let's call this, since it's a centripetal acceleration, let's call this AC. Okay. Now what Newton did is that first he did is that first, what is the time period of moon? That is, how long does the moon takes to complete one revolution around the Earth? That is known to us. Time period of moon is 27.3 days. That is Earth days. So we can convert it into second by 27.3 into 24 hours. Oh, sorry, days. So in Earth day will be 1 day is 24 hours. So 24, then per hour 60 minutes, then 60 seconds. So 24 into 60 into 60, which will give us 86400. This many seconds it takes for the moon to complete one revolution around the Earth. Okay. Now let's say R, that is the mean radius or the radius of moon's surface, is 3.84 into 10 to the power 8 meter. 3.84 into 10 to the power 8 meter. Right. So what will be the velocity of the moon? It will be, see, with a constant velocity of Vm, the moon completes the circumference. What is the circumference of the path? It is 2 pi r. R is given by 3.84 into 10 to the power 8 meter. In how much time? Tm. So this will be 27.3 into 86400. If you solve this, you will get a velocity, orbital velocity of 1.02 into 10 cube meter per second. This is the speed of the moon, speed at which the moon is moving in its orbit. Okay. So if it is so, then the centripetal acceleration can easily be found. AC must be equal to, we know, Vm square by R. Right. Substitute the values. Vm is given by this, R is given by this. So if you substitute the value and simplify, you will get a result which is almost equal to 2.72 into 10 to the power minus 3 meter per second square. Now, after you have found this, you will come to a little bit of a confusion. What kind of confusion is that? On the Earth's surface, we already know that acceleration due to gravity, G, is given by 9.8 meter per second squared. Okay. However, this is acceleration, centripetal acceleration of moon is this, which means that these two are quite different. So why it is so? Here comes the masterstroke from Newton. So what Newton assumed is that the force of attraction between the two particles will vary with the distance. Since the apple was very close to Earth, so the acceleration due to gravity was much, the acceleration produced due to gravity, the force of attraction of Earth on the apple was much greater compared with the force of attraction on the moon, because of its distance from the Earth. So what he assumed is that an inverse square variation, that is to say, he assumed that the acceleration due to gravity varies inversely as the square of the distance between the two bodies. So Earth to moon, the distance is r, so acceleration produced in the moon by Earth will be proportional to 1 by r square, which will mean that AC, acceleration produced in the moon, divided by acceleration due to gravity. Now acceleration due to gravity is always measured very close to Earth's surface. Okay, so this will be 1 by r square, so this will be 1 by r square and 1 by r e squared, but r e is the radius of the Earth. This is r e. So when we say the object is very close to Earth's surface, we can take the distance to be practically equal to the radius of the Earth compared with the radius of the moon. Radius of the moon's orbit. So if we take this, what we will get? We get this is equal to r e squared by r. Now Earth's own radius and moon's radius, radius of moon's path, that is, sorry, this is whole square, 1 by 60. We already know that value. So Earth radius is 1 by 60 times the radius of moon's orbit. So this has to be whole square. So AC by G must be equal to this. So if I say so, then, or if we say so, then AC must be equal to 1 by 60 whole squared into 9.8, since G equal to 9.8. And this will give you, remarkably, almost equal to 2.72 into 10 to the power minus 3 meter per second square. Which means that if we consider inverse square variation of acceleration due to gravity, if we say that acceleration due to gravity or the Earth's acceleration due to Earth on an object varies as 1 by r square, then we have a remarkable agreement of acceleration for the moon and acceleration due to gravity near the Earth's surface. This is one important part of it. Alright, so we have found acceleration is proportional to 1 by r square, number 1. Number 2, Newton also found, or further analyzed and found that the force of attraction between two objects, m1 and m2. These two objects, see, the attraction of an object on the other must be dependent on the mass of the object. As we have seen, Earth has a higher mass compared with the moon, right? So the force of attraction of Earth must be dependent on Earth's mass. He also concluded that these two forces, since they form action and reaction pair, so these two forces must be numerically equal, which means that not only the mass of the first body but the force of attraction between two bodies depend on both the masses. So he concluded that the force of attraction must be proportional to m1 and m2, that is both the masses. He already had found that force of attraction is proportional to 1 by r square, because acceleration varies as r square, so force of attraction must also vary as r square. Combining these two, he found that force of gravitational attraction between two bodies must be equal to some constant of proportionality m1 m2 by the square of the distance between them. This is the mathematical expression for the famous Newton's law of gravitation, where this constant of proportionality is known as universal gravitational constant. So what if this equation, if we have to state it in words? Clearly the equation states that the force of attraction between any two masses or particles in the universe is directly proportional to the product of the masses and inversely proportional to the square of the distance between the two masses. Okay. Now, this force of gravitation is one of the four fundamental forces, as we have discussed in the first chapter only. We said that there are four fundamental forces in the universe: the strong nuclear force, the weak nuclear force, the electromagnetic force or electrostatic force of electrostatic force, and the gravitation, force of gravitation. And this force of gravitation is the weakest of all the four fundamental forces. Okay. So, till now what we have found is a statement, mechanical statement, and also the statement for Newton's law of gravitation. Now, if we say that m1 equal to m2 equal to 1, and we say that r equal to 1, that is two unit masses separated by a unit distance. So, in SI, two masses of 1 kg separated by a distance of 1 meter, or in CGS, two masses of 1 gram separated by a distance of 1 centimeter. Then what do we have? We have F equal to G, from which we find a constant value for the constant, gravitational constant, universal gravitational constant, which says that universal gravitational constant is numerically equal to the force of gravitational attraction between two unit masses separated by a unit distance. Right? Now, what will be the dimension of universal gravitational constant? Force, mass, and distance, we already know the dimensions, right? So, this equation will give us that G must be equal to F r square by m1 m2. So, we have m L T inverse 2 for force, we have L square divided by m and m, which will give us m inverse L cube T inverse 2 as the dimension of universal gravitational constant. M inverse L cube T inverse 2. As for the units, SI unit of universal gravitational constant will be unit of force multiplied by unit of distance divided by unit of mass squared. So it will be Newton meter square per kg inverse 2, and in CGS it will be dyne centimeter square per gram inverse 2. Okay. In CGS. Now, for the values, it has been experimentally found, and the value of universal gravitational constant is found to be 6.67 into 10 to the power minus 11, right? 10 to the power minus 11 Newton meter square per kg square, yes. Newton meter square per kg square, which is equal to 6.67 into 10 to the power how much? If you convert the units, as we did in units and measurements, and we can always find in dyne centimeter, and it will come out to be 10 to the power minus 8 dyne centimeter square per gram inverse 2. You can always verify this conversion, okay? Now, we have been saying this is the universal gravitational constant. Why? Because this constant of proportionality is a universal constant. What it means is that this constant of proportionality does not vary. It will be the same for any two given mass, however small it may be, like probably the mass of these two planes, or however large it may be for galaxies or two black holes or two stars, and so on and so forth. Whatever be the case, whatever be the condition, this constant, this value of this proportionality constant will remain the same, and that is why it is a universal constant. Okay, so we have just scratched the basics of it, the law of gravitation. Now we know that force is a vector, so what we'll need to do is that we'll have to find a way to express it vectorially, and then built from there. That will be for the next video. Okay.